Greetings to everyone. My name is Nikolin Hima, and I am a PhD student at the University of Trento. Together with my supervisors and in collaboration with Seismic, we have been developing and analyzing tensile buckling and post-buckling behavior of triangular structural elements. In this brief presentation, we will share with you the concept that we have developed and how we have utilized the bifurcation in tension phenomena. And in addition, we will also talk to you about our planar lattice that we have developed based on this concept. And also we will dive in very briefly to the structural behavior in the realm of statics and dynamics of this particular system. The concept that we have developed consists on a simple triangular structure that actually is comprised of rigid bars connected with hinges, and a torsional spring is incorporated in the lower right node of the system. In the bar in front of it, we have incorporated a slider, which divides this bar in two equal parts. Slider is actually a device which imposes the same rotational angle and axial displacement to the two connected pieces. And it actually allows for relative sliding, but without transmitting the shear force. This enables the bifurcation in tension phenomena, which was discovered, detailed numerically and also experimentally by the Solid and Structural Mechanics group at the University of Trento. The presence of the slider will fit the system with the single degree of freedom that is able to show this unilateral motion as shown here in this simple animation. By playing with the initial configuration angles and the vertical load applied on the system, we can tune this simple elementary structure to render a structural behavior that can cover a wide range from positive stiffness behavior to negative stiffness behavior. In addition, by combining two of these elementary structures, we derived a planar lattice that can actually exhibit and cover bilateral motion. Analyzing this system revealed that its equation of motion is very nonlinear, and this is the source of its mechanical properties. Initially, because of the presence of the slider, this system will require an activation load of the horizontal load to be applied on it in order to initiate or ignite the motion. Once the motion is ignited, depending on the, let's say, initial configuration angles and the stiffness incorporated in the system can cover a wide range of structural behavior, but in any case, it will be a symmetric behavior. In addition to that, we have analyze the free dynamics of the system by applying an initial perturbation of the system. Eventually, by this initial perturbation, the system will exhibit an oscillatory motion, where one of the layers will bifurcate at a time. But we noticed that as the system was going back and forth at the initial configuration, the layer that was previously bifurcating will eventually lock. This locking will result in an impact which will drain energy out of the system. This energy that is drained out of the system is quantified with the restitution coefficient, which is evaluated with the law of the conservation of angular momentum. After every impact, the velocity will be reduced, which will cause that the consequent amplitude to be lower than the previous one. Therefore, after a certain number of impacts, the amplitude will be reduced significantly until eventually the motion will be completely attenuated. And the period of vibration after every cycle will be reduced with a factor that is a function of the restitution coefficient. In addition to that, the frequency of the vibration of the system is dependent also on the initial perturbation, as can be shown here in this plot. In addition to that, it can be seen that there is a clear relationship between the initial perturbation and the period of the vibration of the system, and the more we increase the initial perturbation, the more the initial frequency will be, let's say, smaller and the period will be higher. In order to evaluate the efficiency of this concept in terms of seismic isolation, we devised a seismic isolator comprised of periodic repetition of our planar lattice and exposed it towards real-life loading conditions with a structure that is comprised of 4 stories. The system was then exposed towards 3 real-life earthquake scenarios, and our numerical simulations suggested that the system is able to reduce the impact of the seismic event by more than 60%, which would reduce or minimize the chances for any damage. And also the profile of the frequency of the vibration of the entire system with the isolated system will be significantly manipulated, which will reduce the contact affection of the materials in the building. That would be all in this brief presentation. Thank you for your attention, and don't hesitate to contact us.